Hi guys, BuildZoid here, and today we're going to be taking a look at another DDR5 overclock. This time I've set it up on the MSI Z690 Torpedo EKX, which uses the same 6-layer daisy chain topology as basically all of the other DDR5 Z690 6-layer MSI motherboards. The memory kit that I'm using is the Corsair Vengeance engineering sample kit that I got sent for the DDR5 overclocking competition. Now, obviously, the issue with this is an engineering sample kit, and I don't really know how representative of retail Corsair memory kits it is. I would assume the main difference between this kit and retail kits is that this is probably slightly better binned on the memory chips. And also, I'm not sure if Corsair is selling the 10-layer PCB that these come with. I'm also not sure how much of a difference that 10-layer PCB makes. So I'll probably end up maybe like retesting the memory settings that I have here right now with the Gigabyte memory kit that I have, because that is also an engineering sample kit, but that uses a pretty standard 8-layer DDR5 PCB. Anyways, the memory sticks are, of course, single rank SK Hynix memory chips, 16 gigabit SK Hynix memory chips. Each stick is 16 gigs. Yeah, the CPU I'm using is, of course, the 12900K, which is on an AIO. And yeah, let's look at the actual. And I have the fan sitting on top of the memory sticks because well, I am kind of pushing them, and so with DDR5, thanks to the power delivery being on the actual memory sticks, they run rather hot. So I would strongly recommend, if you're pushing, more than like 1.4, 1.45 volts into your DDR5 sticks, that you put a fan on them. Because they don't they don't like running hot. It'll help your stability in terms of what you can reach, like what kind of overclocks you can reach, and also, well, yeah, that's the main thing, is it does help with stability. So yeah, I don't really think, like, unless you're going north of 1.5 volts, you wouldn't necessarily be concerned about the actual operating temperatures of the sticks. But yeah, even at lower voltages, having a fan on the memory sticks just helps with stability, because most memory chips have a optimal temperature range where they run best, and generally it's lower rather than higher. So anyway, let's take a look at the settings now that I've shown you the setup that we have here. So for stress testing, we've got 33 loops of LinPack, which it passed. Right, it says right there, passed, so that's all good. This is 10 gigabyte data set size for the LinPack Extreme run. Then 520% of HCI MemTest Pro. Y-Cruncher also runs, right? Like, we can just run it again. This is 2.5 billion Y-Cruncher. Yeah, so LinPack and Y-Cruncher are more like CPU and memory controller stability tests, whereas HCI MemTest is more a stability test of the actual memory sticks themselves. So that's why you want to use a combination of tests like this. Pretty much always. There's a variety of other memory tests out there, and you can actually sort of replace LinPack with Prime 95 with really large data sets in Prime 95, but yeah, I prefer using LinPack, because LinPack has very high peak power draws as well, so it really like heats up the memory controller, and that shows you if you have any like temperature-related memory controller instability. Now, the interesting thing with this board is it was actually very well with this setup, I guess I should say, because depending on the memory sticks and CPU, you might see completely different behavior. But the interesting thing for me was, like, getting MemTest to pass was actually very, very easy, and LinPack was super difficult to get stable. Like, for a very long time, I was struggling to make it past a third loop of LinPack when trying to dial in this memory setup. And there's a very sort of weird reason for that, and we'll get to that when I show you the settings in the BIOS. But yeah, so Y-Cruncher runs quite happily, MemTest runs, LinPack runs. I'm just going to quickly save a screenshot of this just in case I screw up. I've not yet done a retrain stability test, so one of the big problems with the DDR5 when you're pushing it is that you can often get settings that'll work once, and then if you ever restart the system, they won't work again. Or, well, you restart the system, they stop working, then you restart the system a few more times, and they might start working, and like that is super annoying. So I've not yet done a restart stability test. Now for the restart stability test, you basically just have to make sure that it passes 100% mem test. I've not seen a scenario where like it would first like where it passes 500% and then it like errors out after like 200% or 300% on the second pass. I've not seen that. What I have seen is it'll pass like 500% or 600% or whatever percentage of mem test on your like initial run, and then if you restart, it'll error in like somewhere between 10 and 100%, if you have the retrain stability issues. So that's something to watch out for with DDR5. If you've stabilized an overclock, fully power cycle the system, like turn off the power supply, turn it on again, see if it still works properly, because you're generally not going to have issues actually posting. I've not really run into that. Like Ryzen was kind of infamous for, you could get memory settings that you couldn't reboot because they wouldn't post twice in a row. But with DDR5, and actually 11th gen did this when in Gear 2 with DDR4, you can end up in a scenario, well, it basically seems to be some weird thing with the Gear 2 memory controller mode, where, yeah, like if you restart the memory, like it'll always train. Like I've not had it fail to train, I've just had it get into the OS with settings like, and for no longer be stable. So I've not yet checked if that's like if this setup suffers from that, but I'll just leave a comment under the video or in the description about whether or not it is retrain stable. I guess I could also just not post the video if it's not retrain stable. That's also an option. But since I mentioned leaving a comment, I'll leave a comment after I check the retrain stability. And for that, you really do just like power cycle the system like 5 times, and each time you have to run like 100% mem test. If it does that, then it's fine. I've not really seen other issues than that. I have seen it crop up that like you could do, like 3 times and then the 4th time it would fail, but like somebody else who also does a lot of memory overclocking, they use 5 times, and so yeah, I'm just gonna stick to that, because I guess you could just like if you're running a server or something and it's absolutely mission critical that your system is 100% stable, I guess maybe don't memory overclock, or just don't try to run aggressive settings where yeah, like this starts becoming a concern. But for like I'm gonna do 5 checks, like 5 retrains, see if it's still stable, and hopefully it should be. Interestingly enough, you can normally start getting an idea of if you have retrain issues just from the actual overclocking process itself, because your memory stability will sort of randomly come and go between like timing adjustments that shouldn't be affecting the stability as much as they end up doing. So I've not really run into that. Like the main, like basically the linpack issues were constant, and memtest was always fine. So I'm assuming this is not going to have retrain issues, which is why I've already committed to recording this video. Anyway, I've run the Intel MLC, so that's the Intel, the reason I use this instead of IDA is this is a way better memory, latency, and bandwidth benchmark. It doesn't break when you change the BCLK. However, right now we aren't running a BCLK overclock, so I guess we can run IDA as well, just for a comparison point between the two of them. Also, the linpack performance is pretty solid, 627 gigaflops at 5.1 gigahertz on the core and 4.8 gigahertz on the caches. Like, it's not the peak of what you can do at 5.1 gigahertz if you have a 1 DIMM per channel board, like a Unify X, a Tachyon, or a good version of the Apex. You should be aiming for like north of 630 gigaflops with just the P cores and hyperthreading enabled. I don't have the E cores turned on right now, because the E cores make it impossible to run memory stress tests. It's rather, well, not impossible. They make it really difficult to run memory stress tests, and I'd rather not deal with that, especially since they don't change the performance of the CPU that much. Anyway, so here's a quick IDA run. Yeah, so IDA just spits out numbers that are also higher than the Intel memory latency checker for things like bandwidth. For latency, I actually have no idea what to expect right now. I've not been using IDA very much on DDR5 because on a lot of the 1DIMM per channel boards I use a lot of BCLK, and that just totally throws off IDA. Also, one of the issues with IDA is it's kind of inconsistent run to run, so you need to run it a few times to get a... Or, well, yeah, generally you'll want to run it a few times to get an accurate result. And then it went up. It helps to not have hardware info running in the background. Any kind of monitoring utility is going to, like, because any kind of monitoring tool is constantly polling the system, so it actually gets in the way of any kind of memory benchmark like this. Got 54. I'm just going to kill hardware info. But low 50s is pretty good for DDR5 in, you know, Gear 2 with 2T command rate, so I guess I shouldn't complain too much. I'm kind of annoyed that the first latency result was 53 nanoseconds and now we can't get it again. Hey, now we got 52.5. Yeah, so IDA's a very great benchmark. I highly recommend that you use this instead, because the main thing is, like, this won't break when you start messing with your BCLK. It's also very consistent compared to IDA, so you don't have to sit there and, like, rerun it a bunch of times. And it also gives you latency metrics for different levels of memory controller load. That's if you're wondering oops. Yeah, if you're wondering what's going on with this, is basically, like, here's the latency when the memory controller is shuffling around a ton of data, right? Because we're getting like 96 gigabytes of bandwidth. And then down here, we have the latency when the memory controller is actually not doing very much work at all, and so we get a very low latency result of 49.5 nanoseconds with only like 2 gigabytes of memory bandwidth per second. So yeah, anyway, that's the OS result. Like, that's the stability test. And now let's take a look at the actual memory settings in the BIOS. And I gotta say, I'm actually really impressed with the board, because it is a 6-layer daisy chain topology, and so I was really not expecting it to be able to do 6200 megabits per second memory speed. And no, it does 6200 megabits per second just fine. So that's pretty cool, even with my not so great 12900K. Right, fires right up. So yeah, anyway, for 6200, I'm just using the 62x ratio over here with the in Gear 2. And then for the memory settings, I'm not really doing anything special. We just have 2T command rate, which ends up actually being 4 ticks, because in Gear 2, your memory controller uses well, we'll not get into that, but it, like, basically 2N command rate is not the same as, like, 2N command rate Gear 2 is not the same thing as 2N on Gear 1. Let's just put it that way. Not that you can run Gear 1 on DDR5, the DDR5 portion of the memory controller. I straight up think it's not physically capable of running in Gear 1. Like, I don't think it physically has that capability. Most motherboards won't let you even try to enable Gear 1 for DDR5, so it's not really like a real concern. Just make sure that you're not in Gear 4, because Gear 4 is going to tank your performance. Anyway, so cast latency, we're at 30, which is actually really, like, that's pretty low for DDR5. Then TRCD 37, TRP 37. For SK Hynix, this is actually, this isn't as good as it gets. I've seen some absolutely crazy memory sticks out there, but this is really solid. Like 30, 37, 37 at 6200 megabits per second. Like, I don't really have any memory sticks that go below this. Stable. Then we have TRAS 28. It doesn't go any lower. Like, well, the board will let you set that lower, but the register on the actual CPU doesn't go below 28. TRFC of 355, which is a pretty normal TRFC for SK Hynix memory sticks. Then TRFC per bank, we have 255 generally. Your per bank can be about 100 ticks lower than your, main refresh cycle. So yeah, that's 255. Both of these could maybe go a little bit lower, but at this point, it's not going to make a huge difference in performance. Refresh interval is set to 65,000 because it's not giving me any stability issues yet. Technically, you can set that even higher, but, like, yeah, you can set it very high. But I've encountered, well, admittedly, it was just for like benchmarking settings, but I've encountered some weird behavior with completely maxing out the TREFI. Also, some motherboards won't let you max it out. So, yeah, and also the difference, well, there is a, like, this is slower, but I'm less worried about 65,000 causing unexpected stability issues than 260,000. So, yeah, like, there is a performance benefit, but I don't really think it's, like, it's not really that big, and I don't think it's worth it for a 20, like, for a daily setup, I don't consider that worth it. Anyway, TRRDs of 4.7, which I'm surprised, like, on a lot of other setups, I generally go for TRRDs of 4.4. Luckily, with DDR5, we have so many bank groups that this isn't really going to affect your performance too much. Like, 4.4 is just faster, but 4.7 isn't going to really incur a massive performance penalty because with DDR5, you have 8 bank groups per rank. So as long as the memory controller is doing a good job of arranging the data into the memory banks, you're not going to be using the long timing basically at all. So, yeah, and this is a good trick for stabilizing like a lot of DDR5 overclocks. Like there's been quite a few scenarios where I've been like, oh, 4.4 just doesn't really want to work quite right. So 4.7 or 4.6 is an option. I did try 4.6 first, but I was really struggling with LinPack, and yeah, 4.7 is not going to be that much slower. So I'm just like, this could maybe do 4.4 right now, but I've not bothered to figure it out, like find out. It's not going to make that much of a performance difference. 4 active window is set to 16. Cast write latency is set to 30. It might do 28, but the performance difference between just having it at 30 and 20, like, and having it at 28 is not really much of anything. So yeah, I'm perfectly happy to leave that at 30. TCKE at 4. It literally can't go lower than 4, so that's as low as that goes. TCCD is at 7. TCCD long is 11. These don't go any lower than this either. And also all of the timings that I have on auto are timings, like these two timings literally do not actually fit, like there's no WTR register on an Intel CPU. So this is a sort of like legacy setting that, like, you can use this, but you don't have, like, you don't have to, and I don't. TWR is in a similar situation where there's actually 2 other timings in the BIOS that configure your TWR, which is why I have it left on auto. And the value that the board is reading out over here is 96. That's actually incorrect. The TWR right now is, I think, 10, with the way I have it set up. Anyway, same goes for RTP. The RTP readout is also incorrect. The RTP is currently 12, if I'm not mistaken. So, and I'll show that to you in memtweak in the OS. Anyway, now turnaround timings. So 11.7, it literally doesn't get lower than this, and that's same group and different group, then different rank and different DIM. These do not apply in this memory configuration because we have we have one single rank DIM on each memory channel. Therefore, there is no different DIM or different rank. So, because these timings apply to sticks or memory, yeah, they apply to memory on each memory channel. So you have multiple bank groups inside the actual memory, each memory rank. So same group and different group, those apply. But different rank and different DIM do not apply because those are not physically present in the system, so we can leave those on auto. Write to write delay, same group. Write to write, different group. 9.7, these do not go lower. It will not be stable if you try to push these any lower. But yeah, same kind of deal. Same group, different rank, different DIM don't apply. Then we have read to write, same group and different group. These are set to 18. They might do 17, but they probably won't do anything lower than 17. Also, the performance difference going from 18 to 17 is nothing. Like, literally, it's one tick. It's, you might be able to measure it in some very memory sensitive benchmarks, but for a 24/7 setup, I would not bother with that. And then write to read, different group, same group and different group, I have 60 and 48. These can go lower. You might be able to push them to as like 54.46 or 56.46 or something like that. But They tend to cause stability. Like if you try to push them really low, that tends to be kind of hard. And 60 and 48 isn't that much looser than the absolute minimum values that I've ever been able to run for these two. So, yeah, that's kind of that. And then the, different rank, different dim, again, don't apply to this memory configuration. So those are on auto. Now, TWR pre is set to 4, and TWR, where is it? PDEN is set to, WR pre and WR PDEN are set to 45. This actually configures the WR timing, which doesn't exist on Intel CPUs, but like the way the WR timing basically works is if you set your WR timing, the motherboard sets these two timings for you, and if you set these two timings directly, the WR timing is actually calculated from these two settings. So yeah, I just have set these to 45. This is not as low as they'll necessarily go. But they also don't make that much of a performance difference if you keep pushing them lower than this. Then we have TRD pre, which is the RTP timing. This is at 12. It probably can do 8, but yeah, I didn't want to spend too much time, trying to dial this in, so it's on 12. TPPD is at 1. I wanted to have it set to 0, but it won't let you set it to 0, so it's at 1. TXP is set to 4. Which is as low as the TXP timing goes, and this helps your memory latency a bit. So this is and this has like no penalty to stability. Like I've never run into a scenario where setting TXP to 4 has caused any issues. So this is one of those that, yeah, you like if you're setting up your memory, just set your TXP to 4. Like don't even worry about it. Just set it to 4, and then everything else is on auto. Yeah. Everything else is on auto. And there is a lot. And a lot of these aren't even timings once we get down to the lower part of it. Oh, wait, here's PPD as well. Well, it's already set to 0, so I guess that solves that issue. Anyway, now let's take a look at the voltages. So so I've not yet figured out the optimal load line for this motherboard, but to run LinPack of 5.1 gigahertz, the 12900K I have, especially on an AIO, needs quite a lot of voltage. So 1.425 volts with mode 4 LLC. This ends up drooping down to around 1.26 volts when LinPack is actually, running at full load, and that is a perfectly safe voltage range for the CPU to be in. 1.425 idle, 1.26-ish at full load. So that's what's going on with that. And then I do have the VRM switching frequency maxed out, but I'm still in the process of testing that stuff. Like I currently have the oscilloscope hooked up to the motherboard. Originally, I was just planning to do some oscilloscope testing with the board, but then it's like, oh, it's already on the test bench. Let's throw some memory sticks in it. Hey, why not see how the board does with memory overclocking? Anyway, CPU SA is overridden to 1 volt. You don't need a lot of system agent voltage when pushing, like at 6200 megabits per second, yeah, with DDR5, you don't need a lot of system agent voltage because the memory controller is not working very hard. Well, the memory controller isn't running at a very high speed, is the better way to put it. It's actually working harder than with DDR4 because it's shuffling around a lot more data, but it's not going as fast, and so you don't need a ton of system agent voltage to stabilize, milder DDR5 overclocks like 6200 megabits per second. VDDQ is up at 1.4. This is actually, well, I'm not 100% certain that it is completely necessary, but it is safe. It is a bit on the high side. I wouldn't recommend, well, yeah, it's safe. I know the board highlights it red, but honestly, I wouldn't worry about this voltage even if you had it all the way up at like 1.45 volts. Above 1.45 volts, I would start having, concerns about the longevity of the CPU, but 1.4 is perfectly fine. It might be possible to lower this, but it's stable. I don't want to fight it any further, to be completely honest. Like, I'm just happy that it runs. I spent way too much time trying to get LinPack to complete, and the voltages were the actual sort of key thing to getting LinPack stable. So it's like, well, this runs LinPack. I'm not messing with it anymore, even though it might be able to lower that voltage a bit, because it wouldn't really change the CPU's power draw or operating temperature or anything that we actually care about, and it's not going to damage the CPU. Now, CPU VDD2 voltage, 1.3 volts. You definitely do not want to run it higher. Well, Okay, I don't know about... So the VDD2 is an awkward voltage. And the reason it's an awkward voltage is that it sweet spots very hard, depending on what motherboard you have, maybe the CPU. I don't have enough CPUs to verify if like VDD2 sweet spots differently on different CPUs, and maybe the memory sticks. I think it's primarily affected by the motherboard. The reason for this voltage is actually used for driving signals from the CPU's memory controller to the memory, as in this is what the CPU uses to talk to the RAM. And on a lot of motherboards, if you set this too high, basically the signal distorts so much that the memory stick isn't able to do anything with it. So yeah, 1.35 volts of VDD2, like it won't pass LinPack anymore. I also tried 1.25, that also was struggling with LinPack stability, so 1.3 volts seems to be like the optimal VDD2 voltage for this CPU with this memory on this board. I would assume on most 6-layer daisy chain MSI motherboards, you're going to end up in a similar VDD2 range, like 1.3 plus minus maybe 50 millivolts, maybe less. This is a really interesting thing with the VDD2 voltage. There's a lot of motherboards where you really don't want to be running it super high. So yeah, and then there's gigabyte boards where, well, at least then there's like the Tachyon where you can run basically unlimited VDD2, which is kind of interesting how the motherboard memory topologies affect that specific voltage so much. Because it is really like, it just depends on what motherboard you're on, and it makes huge differences. Anyway, then we have the auxiliary, so VCC in rail. I've bumped that up to 2 volts, perfectly safe for long-term use. Not going to harm the CPU, can maybe help a little bit with stabilizing the integrated voltage regulator voltages, which are SA, VDDQ. VDD2 is generated by the motherboard. Then we have the CPU PLL voltage, which I've bumped up to 1.095 volts. This can slightly help with CPU stability, as in like core clock stability. Ring PLL and SA PLL both up at 0.99. This helps with memory overclocking and ring stability. And then 1.05 volts on the memory controller. This just helps with memory overclocking a little bit. These do sweet spot, so don't like, and yeah, they do sweet spot. So don't just like copy my settings, because they'll probably primarily depend on your CPU. Like some CPUs might prefer them slightly higher, some slightly lower. Yeah, and now we get to the memory voltages. So the VDD voltages, so the actual voltage that powers the core of the memory, I have that at 1.5 volts. And this is the voltage that primarily affects your memory timing. So this is the main reason that I can do 6200 megabits per second, 30, 37, 37. If I wanted to try maybe CL28, then I'd probably be bumping these up to 1.6 volts. The only issue with that is that the VDDQ voltages, you might notice, I'm at 1.35 volts. The VDDQ voltage on the memory is used for communicating with the CPU. It drives the signals going back. And more VDDQ, because when I was initially setting up this overclock, I started with like 1.4 volts on everything. Then I went up to like 1.5 volts VDD, 1.45 volts VDDQ. LinPack really didn't like that. Basically, it seems that the memory topology on this motherboard seems to just kind of struggle with very high I/O voltage levels. So yeah, I need to run this at 1.35 and VDD2 at 1.3. Otherwise, it is not going to pass even the first 3 loops of... Well, it'll pass like the first 2 loops of LinPack, and then it'll error out on the third one. So yeah, this is kind of annoying, because this is right at the limit of what I would be willing to use as a as relative voltages to VDD and VDDQ. Because VDD and VDDQ have, I'm assuming they have some overlap inside the actual memory chips. And so if the difference between these 2 voltages is too big, you could potentially damage your memory chips. And so, like, with this basically set up as is, I think this is basically the limit of what the motherboard can run in terms of voltages. Not necessarily certain that it's the limit in terms of what we can do on the memory. Maybe with a stronger memory controller, like a CPU with a stronger memory controller, it might be possible to run 6400 megabits per second. Maybe with just loosening out the primary timings, it might be possible to run 6400 megabits per second. I did kind of experiment with that early on when testing this motherboard. I wasn't making much progress with it, so I gave up on it very, very quickly, because also the higher you push the memory speed with DDR5, the more likely you are to encounter retrain issues. It's less like at 6200 megabits per second, I've not run into retrain problems. At 6400 and especially north of 6400, yeah, like the retrain problems are actually a big problem. So especially on 4DIMM like daisy chain motherboards, like 6400 being retrain stable is I've not managed it yet. I've not yet managed a daisy chain motherboard to do 6400 retrain stable. So that's kind of that. Anyway, so the main thing that like I've sort of discovered with this motherboard is that, yeah, on some boards, like, you're just going to run into I/O voltage limits, where it's like, if I raise the VDDQ, it's not going to be stable anymore. If I raise the VDD2, it's not going to be stable anymore. And that is very, very interesting. It makes sense that it would be like very dependent on the motherboard, because these are these are the voltages that are actually used to drive the signals down the memory data traces, as well as the command address bus is driven with these voltages. So it makes sense that like different boards would have totally different requirements in terms of VDD, like VDD2 and VDDQ. I'm just surprised that it's so drastic. Especially the VDDQ. I really didn't think I'd have to run it as low as 1.35 volts to get it stable, but yeah, no, like at 1.4, it wasn't stable. At 1.45, it was very, very not stable. And I also tried like a huge variety of system agent voltage settings, VDDQ setting, like CPU VDDQ settings, CPU VDD2 settings, and only this combination that I have right now, like, this works. Every other combination I tried, it wouldn't pass LinPack. It would pass MemTest, though, so that was kind of interesting. I'm assuming maybe it has something to do with the actual temperature that the memory controller ends up at, where it's like at low temperatures, the memory controller isn't having issues, but at high temperatures, it just doesn't want to tolerate high I/O voltages, which, yeah, that's interesting. Also, I'm calling it I/O voltage. Well, signaling voltages. The thing is, like, as far as I know, this also actually, like, this does more than just that. Like, VDDQ is used for more than just communicating with the memory, like with the CPU. So I'm not sure that like they're not, like, they're used for, these voltages are used for the signaling, but they're not used for like that's not the only thing they're used for. So, memory I/O and CPU I/O is kind of like the best way to describe them, I guess. But they should not be confused with the old VCC I/O voltage. That one was very different. That one primarily affected the cache clocks. It did not affect memory stability like this. Also, it had like a totally different safe voltage range. So definitely like different voltages, even though, well, voltage naming conventions are just weird. So yeah, that's kind of that. Anyway, so I said earlier that I'd show you how the WR timing is actually set in the OS, so I'm just going to quickly go back to the advanced memory configuration, and here you can see that the board says the WR timing is 96 and that the RTP timing is 24. And now we're going to go into the OS and check with memtweakit if that's actually the case. It isn't. Spoilers. So, capture card pulse. Thank you, capture card. Yeah, so here we are in memtweakit, and you can see my TWR is 10, RTP is 12. And the interesting thing is, like, actually, do I have this enabled right now? So here's a fun one. This should work. I don't like, if you're trying to stabilize your memory overclock, don't change your memory timings in the operating system. That's a terrible idea. But yeah, and then your TWR timing just disappears like that. And actually, if we pull up ASRock timing configurator, it gets... is it bugged out? Where's WR? Oh, there it is. Yeah, see? So WR timing... Because the thing is, there's not actually a WR timing register. on the CPU. So the way this works is actually like the way ASRock Timing Configurator reads out WR is it actually takes this timing and this timing, does some math to them, and then spits out a WR value. Now, that math breaks down when the calculated WR timing is less than 0 or equal to 0. And so you get that because that timing doesn't actually exist. So, and this might even be stable with these two at 32, but I've not run memtest with them at 32. I've not run linpack with them at 32. So obviously that is, yeah, like if you want to experiment with that, knock yourself out, like running really low TWR pre, really low TWR PDEN, knock yourself out if you feel like messing around with that. But I'm not interested in messing with that because, like, I'm happy that this is stable at this point. I am done. At this point, we're just going to do a retrain test and that's it. Also, if you mess with your timings in the operating system, just restarting should reset them. Yeah, which we're going to check right now because on Gigabyte motherboards, they reset. I'm not sure if it should be the same here, but I just want to make sure because I've not really messed with this too much on MSI boards recently. Yeah, so they're back to what they were set in the BIOS. So anyway, yeah, so now I need to do my retrain stability testing. We're just going to fire up memtest and let it run. And that is it for this video. And yeah, I gotta say, like, I'm impressed. Like, if this is retrain stable, I'm impressed. Because I really didn't think that a 6-layer daisy chain board could run 6200 megabits per second on the memory. Like, yeah, actually, here's a clever idea. I can just do this. Oh, wait. And pull up memtest like this. Can just kind of see it in the corner of the video. So, yeah, fan on the sticks, 1.5 volts of VDD, and then really dial in the VDDQ voltage and the memory VDDQ voltage and the VDD2 voltage for the CPU. Because, yeah, that was like the main thing for getting this stable was like having those two voltages at the correct level, because otherwise it just wouldn't run linpack. So yeah, but I am impressed by this board. Assuming that it manages to pass the retrain testing, like I'm really impressed because with the only other 6-layer daisy chain board that I've worked with so far, like 6200 megabits per second is a real struggle. And on this board, it just works, and 64, well, it seems to just work. We'll find out once I'm done with the retrain testing, but like 6400 actually boots very, very easily as well. Didn't manage to get any stability out of it, but it did boot, which is better than like some of the other, like the other 6-layer daisy chain board that I've messed with where it didn't boot. So, yeah, like my expectations are exceeded by this board quite significantly. When it comes to the memory overclocking. So, yeah, I mean, it's still going to be, you know, it's still behind something like a Unify X or a Tachyon. But I was expecting it to struggle with like 6000 or maybe 5800-ish. But no, it does 6200, and it does it with like good primary timings, good sub timings, like... Actually, this is almost like the only thing. This is basically the settings I used on the my really terrible Maximus Z690 Apex, just without the 1T command rate, right? Like the Apex does 1T. I've not had any success trying to do 1T on this board, but even then, like, very solid result in my opinion. So, yeah, thank you to EK and MSI for actually sending this board over. Which I guess I should have maybe mentioned. I've mentioned that in other videos with this board. So yeah, that's it for the video. So thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the AHOC Teespring store where you can pick up shirts, stickers, posters, hoodies, you know, the usual YouTuber merch. And I also have a Bandcamp for my terrible sort of industrial noise metal solo project. So if you don't want merch, you want terrible music, you can get that from the Bandcamp link down in the description below as well. And that's it for the video, so thank you for watching, and goodbye.